So my hope today is to get you guys organized and ready for your test on Tuesday. So let's go ahead and organize the rest of our semester as well. Here's what we've got here. Our test is on Tuesday, covers all of chapter 8. So today, come on, marker. What's going on here? Some sort of look on the board. Today is the 22nd. We are going to review for the test. And we're going to finish chapter 9. Tuesday's the test. And then on Thursday, the 29th, make sure that you understand all of chapter 9. And then May 4th is the last day. So we'll do final exam review. You can review for the final here too. And then May 5th is the study day. Our final exam is Tuesday, May 11th. From 4:30 until 7 p.m. Unless you'd rather have it 4:30 in the morning. Anybody want to do the 4:30 in the morning final?
Is that an option?
No. I can't move the final. It's a departmental exam, so we've got to take it at that time. But my Monday, Wednesday, Friday class decided that they wanted to take it online. Do you guys want to take it online or you want to take it in person? So you can go home 2 hours and a half. That's the last day of finals. That's the last final given on the last day of finals. So I figured most of you wanted to move out, stay home, have mom and dad feed you, do your laundry, that kind of thing, and then disappear from their lives. Right? They see less of you when you come home, right? Okay, so the final exam will be online. This one's in class. And this one's going to be online, but it has to be at that time. So it's a date, right? And I'll have it the way the other ones have been, where you log in on Zoom and I can watch you and make sure that you take this test as if you were taking it in class. No books, notes, anything like that. And you'll be able to do corrections on exam 3, but I don't allow corrections on the final because we got to get her done. And the next thing that students have been asking me is how do I determine their homework grade? And I didn't know that it was vague in any way, shape, or form. We have a homework grade consisting of your top web work grades. We drop 2 of your web works. So your web works are scored out of 100. So for instance, if we've had 14 web works, I drop your lowest 2 and add up your top 12. Then I take your write-ups. I don't know how many we've had, probably 14 of those. Add up all those numbers, divide by the total number of points out of that. So now that's a score out of 100. So I take your 12 web works, I take your score out of 100 for your write-ups. Now there's 13 scores, I average those. That's your homework grade. That's 15% of your grade. Every exam is 20% of your grade. The final exam is 25% of your grade. So if you have been blowing off the web work, or going off the write-ups, turn them in. Turn them in. I'll open web work for you if you request me to, but I'm not going to open unless they're requested. So individually send me an email saying, hey, I'd like to rework assignment, whatever. Can you open that web work? I'll be glad to do that. Okay, so it's a good way to prepare for your final, good way to boost your homework grade, so that I always think the homework grade is my version of a curve. If everybody in here has an A average on your homework grade, then I don't have to worry about curving anything. I don't curve for honor students anyway. You guys get what you get when you get it. Any questions? No questions? Homework questions. Do you have anything you want to talk about on the 8.8 homework or the chapter 9 homework?
Not yet.
Not yet? Putting that off?
Another question
Hey.
on the 8.8 homework.
Okay.
Answer from question 9, it was evaluate the ninth derivative for cosine 2x to the 4th minus 1 over x to the 7th.
And you want the ninth derivative evaluated at 0, correct?
Yes.
So there's f of x. And the hint is don't start taking 9 derivatives of this, as we're talking about. Is that x to the 4th
That's
inside the parentheses?
Yes.
Because there's all kinds of chain rule stuff going on here. So taking 9 derivatives of this as it sits would be quite the bear. It would take you a day or two. You could do it because you're all very good at calculus 1, but it's not worth doing it that way. The hint is to look at the power series for this function. So I'm going to start with the power series for the cosine. So cosine of whatever, remember cosine was the even function. So it has all the even powers of x, including x to the 0. And then it alternates signs, so the next one's minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Next one will be plus x to the 8th over 8 factorial, and so on. Goes on and on and on like that. Now I'm going to substitute where I left those parentheses open, the 2x to the 4th. So this is going to go in here and all the way down the line. Then we're going to subtract 1. So when I subtract 1, it gets rid of that one. Right? Now I'm going to divide by x to the 7th. So let's put an x to the 7th down here. And then we're going to simplify a little bit. And so this will look like, let's see, that'll be a minus 2 squared. That's an x to the 8th divided by x to the 7th. Will leave me an x up here. And the 2 factorial. This will give me 2 to the 4th. 2 to the 4th is 16. That's x to the 16 divided by x to the 7 gives me x to the 9th. Is that right? 16 minus 7. Yep. Over 4 factorial. 2 to the 6th. Oh, I forgot what that was. Someone just leave it as 2 to the 6th. That's x to the 24. 24 minus 7 might be 17. I don't think I need the other terms. That's what f of x looks like. Do you agree with the steps that I did there? Okay, now we're supposed to go through here and take 9 derivatives. Well, the first derivative is going to give me a constant here. So the second derivative of that term will be a 0. But after 2 derivatives here, I'm going to have, let's see, the first derivative will give me 9x to the 8th. The next derivative will be 9 times 8, x to the 7th. The next derivative will be 9 times 8 times 7, x to the 6th. And when does this one become a constant? How many derivatives can I take of x to the 9th?
10.
I can take 10 of them. On the 10th derivative, it's a 0, right? So on the 9th derivative, it's just a constant. What does that constant look like?
16 times 9 factorial.
Where the 9 factorial comes from every time I bring a power down, it's 1 power less than it was before. So I've got this 16, the 9 factorial from taking the derivative of that, and the 4 factorial. These will have x's in them. So all the terms out here will have x's. These will be terms involving x to a power. So when I evaluate that at 0, all the terms prior to this one vanished through the derivative. All the terms beyond that one will still have x's in them. So when I evaluate them at 0, I'm multiplying by 0. So this is the only thing that's left when x is 0. And so there's the 9th derivative when x is 0. Okay? So it really helps if you know the basic power series. Which ones do you know off the top of your head? Do you know the Maclaurin series for I think the easiest one was e to the x. Who remembers what that one looks like? X to the n over n factorial. So if I write it out, it's 1 plus x over 1 factorial, x squared over 2 factorial. Okay. To me, that's the easiest one. I just did the cosine one. But if you can't remember the cosine one, you can get it always from the sine of x. Sine of x was the odd function. So it starts with x to the first power over 1 factorial. And then minus x to the third over 3 factorial. X to the fifth over 5 factorial. And so they're all going to be a bunch of odd terms. And they alternate in sign. So the sign here would be 2n plus 1 over 2n plus 1 factorial. If you can remember that one, then just take the derivative of it to get the cosine. Derivative of sine is cosine, so that would give us the 1. This would give me a 3x squared, but the 3 cancels with the 3 factorial, leaving us 2 factorial underneath an x squared. This gives me 5x to the 4th. The 5's cancel, so my extra 4th will be over 4 factorial, and so on. So the sine of x has as its derivative the cosine of x. So it still alternates in sign. But now it's going to be moved over 1, right? And then this is going to be even.
That last one, you put x to the 7.
Oops, didn't mean that. Even numbers. Then the other one was the geometric series. We know the sum of a convergent geometric series looks like a over 1 minus r, provided r is smaller than 1. And a geometric series looks like a plus ar plus ar squared plus ar cubed and so on. So we've typically written this one as the power series for 1 over 1 minus x. So A is 1 and R is x, and it just looks like 1 plus x, x squared, x cubed, and so on. I forgot the one for the natural log of x, but that might be a good one to remember. That would be, we'd have to move it over, x minus 1 minus x, or x plus 1. We can always figure that one out pretty easily, right? If I want the power series, say, for the natural log of 1 minus x, I just integrate this and change the sign because of u/du substitution. If you know those, I think you can get the other ones, or you can always use the general formula for the Taylor or Maclaurin series to generate the other ones. Okay. And then you can build on for stuff like that. Make sure you know term-by-term operations. Make you think of anything else? Okay, so I think I'll finish chapter 9 first. I'll take probably about an hour, and then give you a little break, and then we'll review for your test. I realize I close yard to the end of the semester until you write it in this much space. We're almost done. What are you guys gonna do all summer? You gonna take classes?
Yeah.
What's the hurry? You trying to graduate or something?
Trying to get out foundation learning.
Oh, there's that. You have to finish your entire core to get out,
Pretty much.
plus physics and chemistry. Well, a lot of folks don't make it as far as you guys made it.
Yeah, my brother switched majors to Cal 1.
Yeah, you either find out that it's not for you or you're invited not to come back. I think, what is the minimum GPA now? Is it still 3.0 or is it 3.2? For engineering.
For engineering, I think it depends on which.
Yeah, petroleum is like 3.6. It's almost impossible to get a petroleum engineering degree. That's cumulative 3.6.
I think for most of the engineering majors, it's like either 2.5 or 3.
To get into it, I know it's 3, to change from another major.
Yeah. But
I think it's 3. Because we get a lot of math majors who are 2.7 students, and they get kicked out of engineering with 2.7.
I just know my friend is like, he's an EE, and he's like, I gotta give above 2.5 to stay in.
Wow. I think they've lowered it on computer science because there's so few computer science majors anymore. Yeah, it's hard. It's hard degree. You guys are in a hard major. But you're doing great, right? When campus opens up again fully and you guys are in Cal 3 or differential equations or linear, and you need some help, my office is in the corner of the math building on the 2nd floor. Come up and I can help you. Linear algebra is easy. Linear algebra is it's a 2,000 number course. You solve systems of equations. We're going to do some linear algebra today. We're going to compute determinants. Linear algebra is easy. There's a bit in there that's a little bit odd because you learned some new language. But other than that, it's easier than Cal 3. Okay, so what we've done last time in section 9.3, we did the vector dot product. Let's see if I got this. folks can see it. I don't. All right, in section 9.3, we did the vector dot product, which was a scalar. So make sure you remember that. That's really the only place you can go wrong. The dot product between two vectors, let's say that that has components A1, A2, A3. We dot it with vector B1, B2, B3. And all you do is multiply the x component with the x component, the y component with the y component, the z with the z, and add them together. So you have A1, B1 plus A2, B2 plus A3, B3. We had the following properties of the dot product. That you can dot two vectors together in any order because multiplication of real numbers is commutative. If you dot a vector with itself, you're essentially getting the magnitude, but it's the magnitude squared. One of our applications of the dot product was it can be used to find the cosine of the angle between two vectors. Oops, I should put a V there. That'd be there. Not that that matters. And from that, we can tell if two vectors make a right angle with each other. Two vectors are orthogonal. If this is a 90-degree angle, which makes the numerator 0. Cosine of 90 degrees, cosine pi has a 0. So V dot W is 0 if and only if, so a double-headed arrow, V and W are perpendicular to one another. Familiar with the little perpendicular symbol? Then we had another application was that work can be thought of as a dot product between the force and the distance that the object moves. Moves from point P to point Q. And then we can also use a dot product to find the projection of vector V onto W, which was given by V dot W divided by the magnitude of W. All of that times W. Where this number in front is called the scalar projection or the component of V onto W. It's a multiple of W, which, right, we drew the shadow of vector V onto W, so it's a scalar multiple of W. It tells you how much in the direction of W the projection points. Let's see if we did anything else. Well, let's just find some things. Let's just do some examples here. Let's let V be the vector 2, 3, 5. And W is the vector -2, -2. I don't know what that number is, -1. Find We find V dot W. Find the cosine of the angle between V and W. And find the projection of vector V onto W. So see if you can use those formulas real quick. Projection is a vector, the cosine of an angle is a number, and V dot W is a number. Something to check with. Here's V dot W. Multiply X with X, Y with Y, Z with Z. And I have 4 minus 6 minus 5. So 4 minus 11, negative 7. Then the cosine is simply that number, V dot W. We've got to make sure it's a number between negative 1 and 1, so we divide by both the magnitude of V and the magnitude of W. So that number's in the numerator. Here's the magnitude of V. Square each component, add them together, take the square root. 2 squared is 4, 3 squared is 9, 5 squared is 25. Now the magnitude of W. 2 squared is 4, negative 2 squared is 4, 1 squared is 1. So that's the square root of 38 times the square root of 9. Maybe like that. Square root of 9 was 3. Then the projection. Projection has V dot W here divided by the magnitude of W. And then you take that number and multiply it with W. So that's not a dot right here, that's a product. Because this part in here is a scalar. V dot W is still negative 7. The magnitude of W was this 3. And then you multiply that into vector W. And you get negative 14 thirds, positive 14 thirds, positive 7 thirds. Is that okay? Negative 14 thirds, positive 14 thirds, negative 7 thirds are the components of the projection vector. You gotta like easy, right? You gotta like easy. The cross product is another type of product you can make with vectors. See if I can move this over. room for the cross product right there. This is section 9.4. The cross product of two vectors is a vector that is orthogonal to the vectors in the cross product. Well, maybe in physics you did something with the right-hand rule. So if my index finger is a vector and my middle finger is a vector and I make their cross product, the cross product would be my thumb. So it would be orthogonal to both of them and pointing up. Then if I have my vectors oriented in another way, if I have this one going right and that one coming at you, then the cross product is, that hurts. Cross product is going to be a vector perpendicular and pointing down. So it just depends on how you hold your wrist. In physics, the direction is important. In math, it's not, because one of the things we're going to use the cross product for was it's going to give us the characteristic of a plane. In order to write the equation of a plane, we need to know a point on the plane and how much slant it has in the x, y, and z directions. Well, it's easy to get a point in the plane because there are infinitely many of them. We can take 2 points and make a vector. So we can take 4 distinct points and make 2 vectors that lie in the plane. Then we take their cross product and you get the vector orthogonal to both of them. That's going to determine the slant of the plane. And that will be used when you write the equation of the plane. Here's how you compute the cross product. So suppose I have those basic ones, that vector v crossed with vector w. Let's say vector v has the a's as the subscripts, a's with the subscripts, and vector w has b's with subscripts. And you're going to get this vector here. I don't want to write it. You're going to get the vector that has its I component, A2 times B3 minus B2 times A3 in the I direction, minus, then you're going to have A1 times B3 minus A3 times B1 in the J direction, and then plus, so I've used 2 and 3, 1 and 3, so now I'm going to need 1 and 2. A1, B2 minus A2, B1 in the K direction. But nobody remembers it from that. That's too hard to remember. We remember it by writing the cross product between two vectors as a determinant. I'm going to put it up over here so you guys can see it. We write this expression here as the following determinant. We put the I, J, and K components in alphabetical order right here. Then if you're using vector V in the first slot, you put its components in the second row. And then that. How many of you have computed a determinant before? Good, then I'm going to show you how to compute a determinant that is a 3x3 determinant, and this one in particular. Imagine, if you will, this thing has the first and first row covered, which means I'm pivoting around this component I. So cover that. First column, top row, and this is what's left as a 2 by 2 determinant. A2, A3, B2, B3, and I said I'm pivoting around the I. Now I move over and do the same with J. J is in the first row, second column. So we cover up the first row, second column, and what's left is A1, A3, B1, B3. And I said I'm pivoting around J. In this method of computing determinant, we alternate signs starting with plus, minus, plus. So this one has a minus here. The next one's going to be done the same way. I'm now going around the K. So I cover the first row, third column, and form the 2 by 2 determinant with the A1, A2, B1, B2 in the K direction. We compute a 2 by 2 determinant by multiplying the diagonals . So for this one, you multiply right here, A2 times B3, and then you subtract the product of the reverse diagonal, and that's where the A3B2 comes from, so you subtract that. And that gives you the I direction. So each of these 2 by 2s do that, main diagonal product minus reverse diagonal product. The J component has a minus in front of it. And then we have A1, B3 minus the other way gives us the A3, B1. That's the J direction. And then the last one is plus A1, B2 minus A2, B1. And that's the K component. So you got to make sure you get a vector out of this. So you'll see determinants again in linear algebra when you're solving systems of equations. One way to solve systems of equations, this would represent then the coefficients in a 3 equation, 3 unknown kind of set of systems of equations. And there's something called Cramer's rule. Maybe you had any of that in an algebra class a long time ago to help you solve a system of equations. And one of the steps is to compute a determinant. You can compute a determinant by picking any row and moving across it like that. So if I had numbers here and I wanted to come across here, then I would have the A1 and the A2 and the A3 there, and I'd cover up whatever row and column that I'm pivoting in. Okay, so let's do this. Let's find some cross products. I want you to find 2, -1, 3 crossed with 0, 7, -4, and then show this vector that you get through the cross product is orthogonal to both 2, -1, 3 and 0, 7, -4. I'm also going to show you that the order matters in which you put them into the determinant. So if I've got them written in this order, then these numbers go in the second row and these numbers go in the third row. Okay, now let's whip out the little 2x2 determinants. So if I cover up this column with the I and the first row here, that's the 2x2 determinant that I'm talking about. Reading across, it's -1, 3, 7, -4. Don't forget the minus sign in the middle. Now I cover up the first row, middle column. And the numbers that are left reading across are 2, 3, 0, -4. Now I cover the first row, third column, and the numbers that are left are 2, -1, 0, 7. And those are in the K direction. Now go forward diagonal minus reverse diagonal in terms of making products. So here, -4 times -1 is a +4. And I subtract. 3 times 7 is 21. So 4 minus 21 is a -17. Now minus. The forward diagonal gives me 2 times -4 is a -8. Minus 0 times 3 is 0. So in the parentheses there, I have -8. Couple that with the minus sign out front, and I get plus 8j. Then the last one. 2 times 7 will be 14. And then I subtract off 0 times -1 is 0. So I get plus 14k. Now, how do I show that that vector is orthogonal to the two vectors I started with? The dot product. The dot product will be 0. So we're going to show that this is orthogonal to 2, -1, 3 by doing the dot product with it. So let me put it in little cute brackets. These folks can see it. Can't. So it's perpendicular to 2, -1, 3 by taking your cross product vector and forming the dot product here. Prove the dot product is a scalar. So I get -17 times 2 is -34. 8 times -1 is a -8. 14 times 3 is 42. And -34 plus -8 is -42. So that does add to 0. And now let's show that this is perpendicular to the other one, 0, 7, -4. We do one more dot product. -17, 8, 14. Dotted with 0, 7, -4. And they get negative 17 times 0 plus 8 times 7 is a positive 56 plus negative 4 times 14. 4 times 4 is 16. And by gosh, that is a negative 56. So one line when I said you get a vector perpendicular to the two given vectors. Otherwise, what use is my thumb in the little picture? It's also a good way to check if you've done your dot product, your cross product correctly. Because there's so many places you can make a mistake. Now I want to see what happens if we do the cross product in the other order. So in the next example, I want you to take this vector, cross it with that one. So next, find 0, 7, negative 4, crossed with 2, negative 1, 3. Tell me what happens. Did I see anything? Is it the same answer? Is it commutative? We get positive 17i minus 8j minus 14k. Oops. Parentheses. So you get the same thing, but opposite in sign. That's when I turn my hand upside down, show you the vectors going in the other direction. So that's going to be true in general. If you change the order of the cross product, you get the same vector but pointing in the opposite direction. Now look at what happens when you cross a vector with itself. Use those two, see what you find out. When you dot a vector with itself, you get the magnitude squared. Cross a vector with itself, you're always going to get the same thing as well. Find out why. What'd you get?
0, 0.
0 the number, 0 the vector. What's the difference?
0, 0, 0.
You're getting the 0 the vector, you're getting the vector 0. 0i minus 0j, or plus 0j, who cares? So you get the 0 vector. Okay, so let's write those down as facts about the cross product. I got room right there. All right. Cross product. Facts. First thing we discovered that V crossed with W and W crossed with V are opposite in sign. Then we found that V crossed with V is always the 0 vector. One of the applications uses the law of sines to find the angle between two vectors. And it looks like this, that the sine of the angle between two vectors is the magnitude of the cross product divided by the magnitude of the original vectors. So I'll just give that as a fun fact. If V and W are in the same plane, well, they will be, you just have to find a plane, then they can be thought of as the sides of a parallelogram. The magnitude of V cross W can be shown to give you the area of the parallelogram whose sides are V and W. So if this is vector V and that's vector W, and we make a parallelogram out of this, it gives us that area. And in geometry, the area of a triangle comes from taking half of a parallelogram. So if I multiply that by half, it gives me the area of this triangle here. 1/2 of V cross W is equal to the area of the triangle that I've shaded in here. Then there's something called the triple product. If I have two vectors in a plane and then a third vector coming out a little bit, that have to be perpendicular to the two of them, we can form something called a triple product that looks like V cross W is a vector. Then I can dot that with the other vector, and I'm going to get a number. If that number is negative, I make it positive with absolute value bars. That's called the vector triple product. It's got our cross product and our dot product, and it yields a scalar. And what you can interpret this as is if you've got two vectors in the plane, they'll make a parallelogram. And then the other vector, U, will be a height. And so if you make a three-dimensional figure out of that with that parallelogram and an opposite face, and then close it in with the sides, you have something called a parallelepiped. A parallelepiped that you're most familiar with is a box, right? A right prism is a box. A parallelepiped is a box that somebody sat on, and it kind of got squished over a little bit. This can be thought of as the volume of the parallelepiped. Now, here's the tricky part. How you spell parallelepiped? There you go. That won't get you too many points in Scrabble. Too many vowels, and P's are worth a lot. So those are our uses. We can find the area of a parallelogram, we can find the sine of the angle, and we can find the volume of the parallelogram. There's also a distributive property that I can think of this as V dot U crossed with W dot U. No, that can't possibly be, because what is V dot U? Scalar. W dot U is a scalar, so I can't take a cross product between two scalars. So we're going to play that game next time. We're going to play vector or scalar, one of my all-time favorite games. I just start writing letters and put operations in here, and you get to decide whether we get a vector or a scalar, or if it's not even possible. I know that's a fun game. You could do it over the weekend. Do I want to tell you anything else? I don't know either. How am I supposed to know? Let me show you how to compute this thing here for a particular example. This is called V cross W dotted with U is called the scalar, just to remind you that it's a scalar, triple product. I'm going to compute this for 3 different vectors by the way it sits here, but I'm going to show you that you can also compute that as a determinant. So let's suppose the components of vector V are V1, V2, V3. The components of vector W are W1, W2, W3. And the components of vector U are U1, U2, U3. I'm going to compute it this way and that way and show you how to do that. So let's make up some vectors. Give me 3 of your favorite single-digit numbers.
1, 1, 1. 7.
Let's make one of them negative so we can at least see what we're doing. You like 7. 7 is what?
0.
How about that? I like 1s and 0s. And let's take vector U. Let's go 2, 4, tricked you, 5. Okay, so let's compute this in the order that we see it. Let's find V cross W first, and then dot that with U. So we're going to find that 2 ways. The good old-fashioned way, and then by computing that 3 by 3 determinant that I showed you. So let's first compute V cross W. You're old pros at it now. You've done 2 determinants. You've done 2 cross products. You should be able to work it out in no time. So no looking. Good. 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 V cross W. Look when you're done, see if you got the same thing. You can also make a quick check that if I take that and make a dot product, you should get 0. So 1 plus 7 is 8. Uh-oh, I don't get 0. I screwed up somewhere.
Is it your 7?
Let's see. That's closed. 1, -1, 0. Minus 1, -1, 7, 0. 1, 1, 7, 1. So that's 0, -7, that makes that plus 7. 0, -1, that makes that plus 1. 1 minus 7 is negative. What did I mess up? I
But
copied
don't you
something down wrong.
subtract the second
Yeah,
bit
it's
of the.
minus 7 times negative
It's
1.
minus negative
Yeah.
7
And
times
then you
negative
flip
1.
the sign because we're subtracting the whole shape.
I think you got it right, because it's a -7, it's a minus -7.
Right, so that's a plus 7 in the middle.
But then there's a
But then there's a
negative on the
negative on
J.
the outside.
There's a negative where?
On the
Here.
whole J, yes.
So minus a -7. Oh, I see, that's a reverse diagonal. So you're right. So you're right. So now let me check my dot product. 1 times 1 is 1. Minus 7 is a -6. Plus 6 is 0. Good. Do I get partial credit? Don't need it. Don't need it. Got my degree. Okay, now we're going to take that. So let's write that with the brackets. And so next, we find that dotted with U, V cross W, dotted with U. So V cross W is 1, -1, -7, -6. And we're going to form the dot product with 2, 4, 5. Remember the dot product's a scalar. So we get 1 times 2 is 2. -7 times 4 is a -28. -6 times 5 is a -30. So I have a -26 minus 30 is a -56. If we put that in absolute value, then we can interpret that as a volume. We don't care. We're going to keep the -56. Is that what you got? That's the first way. Now I'm going to show you how to do it as a 3x3 determinant. We're going to put them in the order in which we're doing as we read from left to right. So this time, all of our entries in our determinant is the other way with numbers. V cross W dot U as a determinant. So we put V right here, W right here, and U right here. Now use the 1, 1, and -1 as you did the I, J, and K. But now you'll be multiplying by a constant. So cover up the first column and the first row, and you have a 2x2 determinant, 1, 0, 4, 5. And now that'll be multiplied by this 1. Then minus again. Cover up the middle column and the first row. So hide the middle column in our 2x2 is 7025. 7025, and that'll be multiplied by that 1. And then finally, the last determinant, cover up the third column, 7124, and that'll be multiplied by -1. And now do it. This one says 5 minus 0 times 1 minus, let's see, 7 times 5 is 35. The other diagonal gives me 0 times 1. And then 28 minus 2 times negative 1. And so I have 5 minus 35. That's 26. That's negative 26. And so that's a negative 30, negative 56. It's amazing. I did it twice. We've been using the first row in computing these determinants, but you'll see in linear algebra we can compute it using any row. For instance, I can put the numbers 7, 1, 0 back here, and then I cover that row. If I want to know what's multiplied by 7, I take that 2 by 2 determinant here. And then for the 1, I cover that up, and it's that, oops, I got to cover that, and that, go there. See what I'm saying? And you do the signs like a checkerboard. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So typically when we compute determinants, especially larger determinants, we try to find a row that has lots of zeros in it, so that saves us some calculations here. You can do any size determinant as long as it has the same number of rows as columns. So you can compute like a 6 by 6 determinant by computing 6 different 5 by 5 determinants. You compute a 5 by 5 determinant by computing 5 different 4 by 4 determinants. I know, it takes a long time, so you want lots of zeros. And so what you're going to find in linear algebra is you're able to do row operations to get zeros somewhere. You can multiply any row by a number and add it to any other row and get a new row. Like if I wanted to get a 0 here, I would multiply the first row by negative 7 and add it to the second row. And that resulting determinant has the same value, but it might have more zeros there. So that's what linear algebra is, just arithmetic, but with boxes of numbers.
Sounds so easy.
It is pretty easy. It's just number crunching. So you computer science people can think in terms of how you would perform these iterative techniques on a computer. Is that good? That's 9-4. That's chapter 9. I finished earlier than I thought I would, so take a little break and then we'll review for your test. Let's see where I put your test review. Guys that turned in some papers, here they are. There. Warm. Shocking.
Are you teaching ours this summer?
I am not. I do all of the Red Raider orientations for our department. So I welcome the new freshmen in with open arms.
My orientation last year was on the day of graduation.
Was it?
It was a really hectic day.
Dang.
Isn't it online?
It was last summer. I'm going to try to make it face to face as much as we can this summer. Because I bet you guys never even met your advisors.
Nope.
Even to this day, you have no idea who your advisor is.
Nope.
I was on ZipRecruiter for like 4 hours.
4 hours, holy smokes.
Do you think they'll get rid of masks next semester?
I do.
They better.
If you guys do your part and go get you and your family vaccinated.
Bro, second dose the other day.
Oh, yeah.
Good deal.
Yes, sir.
No problems today, huh? You're feeling good?
There were never problems. I'm just built
That's
different.
fantastic. You youngins don't get problems.
I still want to pass out after the second shot. Like, you know, the waiting area?
Yeah, the 15-minute.
Yeah, I saw a woman like just slide out of her chair.
Drama queen. She
Yeah.
was fine.
She was overreacting.
Probably.
She wasn't built different.
She was.
I mean, it's real easy if you're got like old people in your family, do it for them. Nah. Grandma's got a big will. Let's go hug grandma. Right?
I'm just cashing out early.
Yeah, I think they gave the order for all faculty to return to campus over the summer. So all those folks working at home now got to come back to work. They're kicking and screaming.
They're like, no.
No, I can't button my pants.
Okay, important question. Leisure pool.
Yeah, I've been asking about that too.
Like the
The leisure pool and the basketball courts.
Well, I talked to somebody and they said like they're gonna turn off the river and like section.
Oh my God.
And you can
It was
stay in your
fascinating.
section.
I mean, they got
Yeah.
beach volleyball. Why can't they
They've
play
got mini
basketball?
pools
You know?
in the river.
That's pretty funny.
I hope
Yeah.
they don't do that.
That'd be pretty funny.
Like the lap pool open.
Lifeguard, there's somebody in my section.
Like the whole rec is open, right? Like the whole gym is open. But they won't open with a pool. I don't know.
Well, you can't play basketball. You can't do things in crowds. I think the odds of getting,
Play volleyball. though.
Yes.
They're every Friday, 6:30. They're out there. Boom.
I don't understand how they decide what you can do and can't do. There's really no science
They
to
just,
that.
send it through the vibe check. Like,
Yeah.
Right.
They have this wheel that they spin and when it lands on, now we can open volleyball
It's like,
courts.
yes, you landed on my sport.
Yeah, I don't know. I don't know.
Is the test hard? Is this coming one? It's a legit
I'll
question.
say that.
The test that usually has the lowest average is the first one. The test that usually has the highest average is the second one.
That's not good.
So the third one is right in between,
Uh-oh.
I don't like that.
usually.
By a high school student in geometry, how would they rate?
By a high school student, John, they'd be so clueless.
They don't know what a power series is.
I don't know what power series is.
Uh-oh.
It's in the Avengers. Oh no, here comes the power series.
Right.
That is the answer to the test.
Yeah, just like put the Avengers down. It's like, well, Miss Schovanec said so.
Well, let me see. It starts with section 8.1. So if I wrote down some sequences, could you tell me if they converged and what they converged to?
Maybe.
Well, what do you do? What do you do when I say, what does this sequence converge to?
Take the limit.
Take a limit. So if you're good at taking limits, then bam, no problem. Right, so. So the first question, converge? What? If it does converge. So let's look at 3n, n I said, 3n plus the square root of n divided by the cube root of n plus, I don't know, how about 5? And boom, it's easier to do than writing it down.
And it just all be sequences?
All sequences?
Yeah, every single question just be sequences like that.
Yeah.
Exactly.
But like that, don't.
Like all however many.
Know what
Just
you
that.
got to do up there.
Actually, let's make the test a little bit harder and ask one of the questions be different, like
Right.
And you'll write it backwards or in binary code or something.
I mean, I forgot how to spell my last name once, so.
I still can't spell my last name. Ladies, watch out who you marry. Looking for this orphan named Smith. Couldn't find him.
What was your maiden name?
Jarvis. Spell that one.
Like,
Jarvis. Boom.
so from the Avengers,
I
Yeah.
didn't, I have never watched the event.
it's Iron Man's AI.
You said.
I know, but I don't watch it.
Oh, man.
You had summons.
Children.
When they were little, we watched Disney stuff. I watched every Star Wars and every, what was that other one?
Harry Potter.
Harry Potter, I read all the
Star
books to them.
Trek.
They didn't do Star Trek, but what's that other one with the little,
Spaceballs.
no, who's the
Space
little,
Jam?
they were going after the ring and there's that little.
Lord of the Rings.
Yeah, duh.
They were going after the ring.
That one always put me to sleep.
Michelle, Nick, you gotta give us a little bit more than just like, you
The
know,
little dude.
a little guy.
What did he say?
It was just precious, that's all I know.
Oh, that's the word. Word diverge. Yes? Yep.
Do we have to explain why diverge? Or can they say like diverge?
You got a 50-50 shot.
Say diverge, just trust me.
Diverge, because trust me.
Here's curiosities.
That's where you have to do the E. That's like E to the whatever on the right.
Which means it has to converge, because E is something.
But I said to what? Not to either whatever.
Half right, partial credit.
You call yourself an honor student. You only want to get half credit?
I mean, it's better than no credit.
Got a point
I
there.
got the honors.
But we want full credit. We want to be the one that gets this problem right.
You just spell it.
You're going to use Middle and do it. Do it on paper.
I'm sorry.
So Z goes to infinity. The term in here goes to 0. So I have 1 left to the infinity. So that is your clue to use a natural log. Put some letter over there and take the natural log of both sides. Put it here and here. Commence your steps. Let's see what you get. You're going to get an E to the something. Let's figure out what the something is. Go way back this way. So what was your favorite Disney movie growing up?
The Lion King.
The Lion King's good.
Long.
That was beyond my boy's youth. Plus it was a chick thing. We had to do dude things.
Beauty and the Beast.
Beauty and the Beast, I like that one. We did watch that one, but that was a chick thing. I had to have them explore their feminine side.
The one with the, it's about like it's, he wasn't Aztec, was he? No, no, no. No, it's like this guy, but he's like,
Isn't it
oh,
like-
is that what it's shit?
Oh, yeah. Emperor's New
Oh, yeah.
Was Cars Pixar or Disney?
Cars is
Cars is
Disney
good.
Pixar.
They're all the same to me.
Yeah,
Cars
Pixar,
are-
Pixar's the art.
No, I didn't say I enjoyed it, but I watched it over 100 times.
See, you guys are too old for the Teletubbies.
No, we're
no,
not.
I-
You watch Teletubbies?
I can't, not
There was a
vacuum
building
cleaner.
outside my house when I was younger, and I was like, that's the Teletubbies building, and it wasn't.
Creepy, creepy, creepy. You watch some of those old Disney movies and talk about politically incorrect? Oh my God.
Isn't the baby in the Teletubbies movie like 30 now?
She has a kid. She has her own baby now.
What?
Somebody rubbed the tummy.
Oh, no.
What's the E to the what? You got it yet? Quit talking.
I'm trying.
But you're supposed to be doing math while you make conversation. Multitask. Let your mind go on autopilot. All these steps you know, you've done them 1,000 times, or 4 times.
I do a bunch of flipping and stuff.
Can't flip and talk.
No.
I don't remember.
You can come up here and do it, and I'll talk you through it.
Oh.
I don't know.
Chamber
I'll do that.
Multiplier add.
I bet.
All right, right clearly.
Okay, oh, no.
There's the trick. Okay.
Oh, I've never been this close, okay. So,
A different feeling, huh?
this, right, like
Correct.
that, and then you have,
The infinity with 3 loops, I like that. That's a bigger infinity with 3 loops on it.
that's worse than mine. Like this, is that right?
The 4n comes in front of the natural
So it's
log.
out here,
Yeah, put it in front of the natural log so it doesn't look like you're taking the log of it. There you go.
okay,
Perfect.
so now, that's this thing, right,
Correct.
boom, and then you flip it under,
Yep.
so you hit them with the. Whoops.
Okay.
Right, like that,
Uh-huh.
and then so now you have this over this,
Correct.
and then you take the derivatives,
Correct.
and this is where things get interesting. So you got 1 over times, I think it's like -2/3n squared, right?
Correct.
Divided by maybe 1 over 4n squared,
Uh-huh.
and then you do your flippies. This is still equal to this.
Okay.
I feel like my handwriting's getting smaller.
It is, it's like minuscule.
We're gonna maneuver over here.
Okay.
You got so much.
So now, this becomes something like -2 over
Uh-huh.
times 3n squared.
Correct.
This is multiplied by 4n squared over -1.
Beautiful.
So you just combine these things together. So you have -8n squared over 1 plus 2 over 3n times 3n squared times -1.
Okay.
So the negatives cancel
Good.
out. And then you can just take the limit of this.
So cancel the n squared still. Now you can take the limit of that.
Okay, so now I have to rewrite
All
it.
right.
It's like my rule. And then the 1 just is
You got
1.
3 still.
Oh yeah, times that 3.
There you go.
And so I guess if you distributed this,
You don't need to. Go ahead and take it up to infinity.
okay, so this becomes, this right here goes to 0,
Right?
which means you just have 3, because it's 1 plus 0 times 3, so 8 over 3.
8 over 3.
And that's your limit.
That's the natural log of your limit.
Yeah, so you have L is ln. I forgot what this means.
That's
I got
natural
this
log of
far.
L is 8/3. That's what you have now. Natural log of L is
Okay.
8/3.
Okay, I remember now. And then we raise things to e. So the e to the 8/3
Uh-huh.
is equal to L.
There you go. So the sequence converges to e to the 8/3.
Boom.
That was awesome.
Yay.
Awesome.
Thomas ran out of space.
That's why he started just writing small.
That's right. My
Start
paper's,
write minuscule.
my notes, it's big, and towards the bottom, I don't want to go to the next page, so it gets smaller.
He did all this left-handed. Okay? So maybe you can see the general pattern, what it's going to be. Where does the 8 come from? And where does the 3 come from on the E?
Oh, so it's the top times the coefficient of the big thing up there divided by coefficient of the bottom.
Looks like it,
What if we had 3 and squared instead of 3 and? That change?
probably.
Well, it's not that small.
Dang, bro, that is small. Whoops.
That is.
So
Any
much bigger
questions?
when I'm standing next to it.
If we can tell that it's like to the 8/3, like you just said in the pattern, do we have to do all the work on the test?
The only problem is if you say it's 8/3 and it's 7/3, I can't give you any partial credit.
You got this.
So if you're big and bold, go big and go bold.
Hey, just make sure you got your patterns right.
Yeah, so don't strip your pattern. But since when is getting the right answer the most important thing? Being able to do the steps is the important thing. Right. Okay, so now we start with series, and if the series converges or not. So you've got a bunch of things to look at. So now we're going to look at these series. You can tell me this, converge or diverge. And so my first one is going to be diverges by, diverges because the limit doesn't go to 0. We just saw the limit doesn't go to 0. So this diverges by the test for divergence. The limit is equal to e to the what? 8/3, which is not 0. Okay. What about, same question, converge or diverge? And the answer, if it converges to what? My first one. And then my second one. The first one converges to 0. Doesn't have to. Limit goes to 0, tells us nothing. Right, that limit's 0 by the tower of power. The limit going to 0 on a series tells you nothing, other than you need to try something else. What else are you interested in trying?
Geometric series.
It is a geometric series. Because if k is 0, I get 1. If k is 1, I have 2/3. If k is 2, I have 2/3 all squared, and so on. So this is a geometric series. Now tell me everything you know about it.
R is 2/3.
R is 2/3.
A is 1.
A is 1. And so what's the sum of this geometric series? What does it converge to?
1 over 1 minus 2 thirds.
1 over 1 minus 2 thirds. 1 minus 2 thirds is a third. 1 over a third is 3.
Those are the easy ones.
Those are the easy ones.
There's always something whack.
All right. Converge or diverge into what if it does?
What happened?
What happened? Why? Telescoping. Let's write it out and see how it telescopes. Let's write the nth partial sum. So we'll write out all the terms all the way up to k is equal to n. So if k is equal to 1, I have 1/3 minus 1/2. Now k is equal to 2. I have 1/4 minus 1/3. Now k is equal to 3. I have 1/5 minus 1/4. K is equal to 4. I have 1/6 minus 1/5. And then we'll stop out here to k is equal to n. Let's see if it does indeed telescope. Take the parentheses off and see what you can combine. So let's see, it looks like I lose my 1/3. I got a 1/4 minus a 1/4. I got a 1/5 minus a 1/5. Do you think there's going to be a minus 1/6 somewhere down the line?
Oh, yeah.
So let's see. What's going to be left at the very end there?
Minus,
Looks like this one's going to be left. Or is that one going to be left?
That one.
Doesn't really matter which one's left, right? I think this one's going to come out because the minus is always the second one, and that one's going to be left. So I think we can write Sn as -1/2 plus 1 over n plus 2. And now we take the limit as n goes to infinity, because that's a sequence now. That's the general form for the sequence of partial sums. And so we get a -1/2. Sequence of partial sums converge. To -1/2. So this series converges to -1/2. The sequence of partial sums converge, and so does this series. And to the same thing. So those are the ones that were early on in section 8.2. Telescoping, geometric, and the test for divergence.
would the answer have been the same if we crossed off the 1 over n plus 2 instead?
It would.
There would be a situation where it would have.
But you see, the second one is always going out, right? This
Yeah.
one went out with that one, this one went out with that one, this one went out with that one. So somewhere there's gonna be one that goes out with that one.
Okay. But there's also one that goes out with the first one.
Not in the last one, it won't.
Oh.
That's why I tried to write out so many,
Yeah.
so that you can kind of see which one's going to be right. Okay. Okay, now I'm just going to give you some, and you can tell me whether it converges or diverges and what you're using to make that determination. Oh, let's see how many I've got here. Okay, so test each of the following for convergence. Be sure you show all your steps. I think these are somewhat quick. Take your time and see how many of these converge and how many of them diverge and why. Ooh, right here, I think I put the wrong C's. I'm done. Get them in my head. That means all of them are wrong. See, like you did the 13. How many of your series tests can you even name?
Like chapter.
You've got, think about the order which we covered them. Right? Eighth group test, ratio test. That's not the order which we covered them, but those are your favorites. Limit comparison, direct comparison. Test for divergence, integral test. Any others? P series, Q log series, geometric. I think we got about 9 tests that we can use.
So when will we take the anti-derivative? Is that the?
That's the end of the test. Who's done part A already? What happens is K goes to infinity. It goes to 1, right? Test for divergence. That one diverges because the K term doesn't go to 0. Test for divergence shows part A diverges. That's what you would write right there. I'm going to do the test for divergence. I take the limit. I get something other than 0, so it diverges. That's what I mean by show your steps. Okay, so you said your next 2 most obvious series were a P series and a Q log. I got a P series and a Q log looking at you here. This is a P series. And that's a Q log. Right? Oops. The first one's not. First one I simplified wrong. Well, let me make that a -1/2. How about that? That's okay. Right? It's still P series. What kind of P series you got here? Diverges, because K is smaller than P smaller than 1. What kind of Q log you got here? Divergent. Divergent plus divergent is divergent. Divergent plus divergent is divergent. You could have also done a comparison test, right? You could have compared that to, I don't know. You could have said just for divergence again, right?
Is it wrong to just say that it's like top heavy?
Top heavy, so that's the test for divergence. It goes to infinity. Okay, part C, you did a ratio test? Doing a ratio test? Got that it converges? Okay, extra credit, what does it converge to? Nope.
And you're getting that.
Think about the power series, x to the k over k factorial. What function has that power series? No,
EDX.
that's e to the x. So what am I using for x here? No. X to the k over k factorial is e to the x, right? Converges to e to the x, so this converges to e to the 2.
Oh, I see.
This, when we were doing power series, we said that was the power series for e to the x. The Maclaurin series. And so this should converge to E squared, but you can show it converges by the ratio test. You show the limit as k goes to infinity, and 2 to the k plus 1 over k plus 1 factorial times k factorial over 2 to the k. What cancels? What's left after you do your canceling?
2 over k plus 1.
2 over k plus 1, correct. What's that limit?
0.
And in the ratio test, limit smaller than 1, what's your conclusion? Well, duh, converges. Okay. All right, what's left to try on part B? Say it again? Integral test. Integral test is easy when you have a logarithm on the bottom and a 1 over x on the bottom, or a logarithm. It's not a q-log. So I let u be 1 over, let u be the natural log of x, and du is 1 over x. If you integrate from 2 to infinity, 1 over x ln x dx, u is ln x, du is 1 over x. And so you're integrating from 2 to infinity, 1 over u du, which is logarithm. So the log of u, but u is the natural log of x. From 2 to infinity. And when you put infinity in there, I get infinity. So the integral diverges. So the series diverges.
With the integral test, what the integral does is what the series does.
The integral does what the series does what the integral does, yes. Yes, yes, yes. So it's divergent. The integral diverges because it comes infinite when x goes to infinity. So the series diverges.
What if we got just a normal number? Then would it converge?
If you got just a regular, if that was in the denominator, like if I had this, if we did this, that one's going to converge. Because this one would be squared, and we'd be integrating that, which would give us a negative 1 over u. Right? So if I had that, I'd have a negative 1 over the natural log of x from 2 to infinity. So that gives me negative 1 over infinity minus a negative 1 over plus a negative 1 over natural log of 2. So that would converge. If I had changed it. Squared would converge. Without the squared, that ended up in the numerator, so it diverged. Okay, let me see if I can find you something to. We didn't do any comparison test yet, so let me give you a giveaway comparison test. See what comparison test you can use on this one. Try one of your comparison tests on that one to see if it converges or diverges. The giveaway that it's a comparison test is you got all these polynomial type terms. You got a bunch of k's everywhere, then limit comparison is probably the choice. That's my suggestion. Try the limit comparison test and then tell me what your conclusion is.
How do we know what to make it compared to?
Throw away the constants and keep everything that has a K. Throw away the 3 and the 5, and let that be your BK. Decide if BK converges or diverges, and then take it from there. All right, did you get it converged or diverged? Diverged. Pick BK to be the series that looks like 2K divided by square root of K times 2K. So that simplifies to this divergent P series. This P is a half. And so if we do the limit comparison test, we take the limit of the given series divided by the known series. And if you get a positive finite limit, both series do the same. So we're going to take the limit of 2k plus 3 divided by square root of k, 2k minus 5 divided by bk. The square roots of k will cancel, leaving us with 2k plus 3 divided by 2k minus 5. What's that limit? That limit is 1. Remember I said if you get any positive finite limit, both series do the same. Therefore, series converge, series diverges. Okay. Yes.
You also do a test where it's like bigger than divergence, smaller.
Let's see, did I make this, is this, when I threw away the 3, I made the numerator smaller. When I threw away the 5, I made the denominator bigger. Smaller divided by bigger makes this smaller. So that is bigger than divergent. We could have done a direct comparison test. Very good, very good. Okay, Suppose this thing here is a positive term series. Satisfying that k to the 3/2 times ak is going to be smaller than 1 when k is bigger than some big number m. Does AK converge? And why? Because? You're right, because give me a reason in terms of one of our tests. This is one of our tests, kind of looking at you in disguise.
I mean, if it's smaller than 1, when it gets to a big number, it's still going to keep going down if it goes past that big number, which means it's eventually going to
Could be hanging around 1.
It's a smaller than
It could be hanging around 1, but smaller than 1.
Is this actually a limit comparison test?
It's actually a direct comparison test. Right, if I solve for AK, it says that AK is smaller than 1 over k to the 3/2. And the series 1 over k to the 3/2 is a convergent P series. So this says smaller than convergent is convergent. By the direct comparison test, smaller than convergent is convergent. Suppose you could have made a limit comparison test out of it, saying that AK divided by 1 over k cubed is smaller than 1. Okay, next. Next is this. What is the difference? What is absolute convergence? Oops, can't spell it. What is meant by absolute convergence and what is meant by conditional convergence? You want to take a shot?
It always converges when it's absolute.
Well, that absolute refers to absolute value.
And when you put it in the absolute value sign, it always converges.
Yeah. This series is absolutely convergent if the positive term version of that is convergent by one of our tests. The series is absolutely convergent if an absolute value series is convergent. What is conditional convergence?
It's not absolutely convergent, but with a oscillating.
So this way, this is not convergent, but this is convergent. That's conditional convergence. Converges without the absolute value bars, but not with them. So my next question is absolutely convergent, conditionally convergent, or divergent? -1 to the k over 2k plus 5. First, take a look at that series in its absolute value and decide whether or not it converges in absolute value.
It doesn't because if you compare it to a P series, power one.
Okay, so the answer is no. Compare to the series 1 over 2k, which is a divergent P series. Do the limit comparison test. The limit k goes to infinity. 1 over 2k plus 5 divided by 1 over 2k. You get any positive finite limit. Both series do the same. So you have a divergence, so the answer is no. Okay, so we took care of the absolute convergence, so it's not absolutely convergent. So your next step is to check for conditional convergence. How are you going to do that? Using the alternating something test. What are the two steps in the alternating something test? See if the limit goes to 0 and?
The terms are getting small.
Yep, decreasing and limit goes to 0.
I still don't understand how, if the limit goes to 0, why it's not always decreasing. Or how there would ever be an instance the limit would go to 0, but it would be decreasing.
Yeah, I can't think of any examples off the top of my head. Right, so here's the limit going to 0. And I don't know, that's not really decreasing. I don't know. That's decreasing because the derivative is negative. Okay, so our conclusion is conditionally convergent. So same instructions. Absolutely convergent, conditionally convergent, or divergent. How's that? So we don't always have to do this to check for absolute convergence. When we've got k powers and factorials, we have a general ratio test. So try the general ratio test. You want to see if the limit in absolute value of ak plus 1 divided by ak is smaller than 1 or bigger than 1. Smaller than 1, it's absolutely convergent. Bigger than 1, it's not absolutely convergent. And then you can check for conditional convergence. Get a decision yet? Remember how those factorials cancel?
It's converted.
L is 0.
Your limit is 0, that's what I was thinking would happen. Let's see, when I put it as an absolute value bars, the minus goes away. It'll cancel in one of your subsequent steps. I can leave it in there if you left it in. Did you leave it in or take it out? All right, so we have a 3 to the k plus 1. K plus 1 plus 1 will give me a k plus 2 factorial. This is 2 k plus 1 all factorial times the reciprocal 2k factorial. 3 to the k plus 1 factorial. And so the 2k plus 1 factorial simplifies to 2k plus 2 factorial. And you know the 3 to the k's will cancel, leaving us with a 3 right there. That's 3. Now, which one of these is bigger, k plus 2 factorial or k plus 1 factorial? So how does it cancel? Yeah, just use your k plus 2 right there. Same deal with the 2k factorial and the 2k plus 2 factorial. This is the smaller one, so it's going to cancel entirely. And what's left with this? Good. Okay, that's all that's left, period. and everything's now positive, k goes to infinity, and this limit is 0. So it's smaller than 1, that makes it absolutely convergent. Okay? Okay, do you remember then the formula? Oh, wait a minute, we need interval of convergence problem. Let's see, do we have time? Let me find a small one. Find the interval of convergence. Of the power series. Two to the k, x minus 2 to the k, divided by 3 to the k. The interval of convergence on that one, and if the endpoints are open or closed, or mixed. For the interval of convergence, you solve for x where the ratio test is smaller than 1. The general ratio test is smaller than 1. Solve that for x. So good. Keep going, now check the endpoints. That's what you're solving right there for X. So I'm pressed for time. I'm going to cancel the X minus 2 to the K. Leaves me an X minus 2 on top, which doesn't depend on K. I pull it out here. Cancel the 2 to the K. Cancel the 3 to the K. And I'm left with the limit as K goes to infinity. I'm going to have a 2 to the 1 here and a 3 to the 1 there. So I get that as 2/3. It says that X minus 2 in absolute value has to be smaller than 3/2. That means I'm in a 3/2 interval around X minus 2. And so if I add 2 to both sides, 2 is the same as 4/2. So if I add 4/2 to 3/2, I get a half here. Add 4/2 there, I get 7/2 there. Now let's check the endpoints. So we go back here one at a time and put those numbers in. So let's let X equal 1/2. And we look at the series 2 to the K, 1/2 minus 2 to the K, over 3 to the K. Again, 2 is 4/2, so 1/2 minus 4/2 puts a negative 3/2 in there. I can take that -1 out as a -1 to the K. I can write that as 3 to the K over 2 to the K. And so the 3 to the K's will cancel, the 2 to the K's will cancel, and we're left with this. And that diverges because the limit does not go to 0. So that endpoint is open. Let X equals 7/2. We get something very similar. 7/2 minus 2 in here. 7/2 minus 4/2 gives me a 3/2 in there. Which is 3 to the K over 2 to the K. So again, this series is just adding a bunch of 1s together. And so since that term doesn't go to 0, test for divergence shows that it diverges on that endpoint, which makes the open interval from 1/2 to 7/2 is the interval of convergence. So the other couple of things to know are make sure you know the formula for the Taylor series. So the example I was going to work is on the review sheet that I have posted on Blackboard. Find the Taylor series for f of x is x times the natural log of x, centered at c is equal to 4. So you can't use a general formula, you got to just take derivatives. And then make sure you know how to do the stuff like we started with that web work problem. Find the 9th derivative of, cosine of 5x minus 1 over x to the whatever. Okay. All right, there is a review sheet with solutions posted on Blackboard if you'd like to go through it. And I'll be around Friday and Monday if you have questions on that.